Hi everyone, welcome to LC Math. Today we'll be discussing the fact that the derivative of the sine function is the cosine function in a number of ways. So we'll be talking about d by dx of sine x being cosine x. Everybody knows this from elementary calculus. We're going to discuss a few ways that you do see in a calculus class. One that you might not, but that's easy to remember, and also one that I've never seen before, and we'll see how it goes, and you'll definitely tell me which one's your favorite. We'll start off with the most elementary derivation, the one that you typically see. We'll be needing the following limits. We need the fact that sine x over x goes to 0 as x goes to 0, and that cosine x minus 1 over x, this one goes to 1. This one goes as x goes to 0. You can see these by simply looking at the graph. That's the physicist way of doing it. You can also use elementary trigonometry, which we're not going to do now, but you can find it in any calculus book, no problem. Start off by just calculating the limit. Derivative of the sine function is 1 over epsilon. F, you don't need F, that's in general. Sine of x plus epsilon minus sine of x. Notice I'm using the physics notation here where epsilon is an infinitesimal. Basically it saves you the trouble of writing limit as h goes to 0 everywhere. Now we need the sine of x plus y formula. I can never remember this, so I'll just derive it for you the way that I always do. So we have, considering e to the I x plus y here, the real part is cosine of x plus y, and the imaginary part is sine of x plus y, is, by the property of the exponentials, e to the ix, e to the iy, which is cosine x plus I sine x by Euler's formula, cosine y plus I sine y as well, multiplying these out. Real parts. We got cosine x, cosine y. Now we have the imaginary parts, I. We have the cross terms, I cosine x sine y. Other cross term, plus sine x cosine y. Important not to get these confused. One cross term here, cosine x sine y. Other cross term here, sine x cosine y. This one is just a cosine of x plus y. And this one is just sine of x plus y, which is what we need. So we'll just apply this formula up here with y being epsilon. 1 over epsilon. So we have cosine x sine epsilon plus sine x cosine epsilon minus sine x. Okay, and now we're going to separate the expression into terms involving cosine x and sine x, similar to what we did down there, but everything is real. So we're going to distribute the 1 over epsilon as well. The cosine of x terms, well, there's only one, sine epsilon over epsilon. And the sine of x terms, we have this one here, cosine epsilon over epsilon. This one here, which is 1. Should look familiar. We can use the limits that we did not prove up there to show that this one is 1. And this one is 0. So the entire limit is just cosine of x. And we're done. We have that d by dx sine x is equal to cosine x. Definitely seen this before. Probably not in this notation. Just allows you to save yourself some writing, because I don't know about you, but I hate carrying around limit as this goes to this around, and physicists are lazy, so that's why that's done. Not any great philosophical implication, but simply out of laziness. All right, now let's talk about the power series. So what we're going to do now is define sine and cosine by their power series. differentiate the sine series and show that it's the cosine series. All right. d by dx of sine x is d by dx of sum, and is going from 0 to infinity, minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So recall the sine function series contains only the odd terms, which is, we're going to differentiate this here, n equals 0 to infinity, negative 1 to the n, 2n plus 1, x to the 2n, over 2n plus 1 factorial still. Now we're going to simplify the factorials by noting that 2n plus 1 over 2n plus 1 factorial is simply 2n plus 1 here times 2n factorial, since obviously n factorial is equal to n minus 1 factorial, fundamental identity of factorials. Cancel these, 1 over 2n factorial. So this becomes sum from 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial, only the even terms, which is just the cosine series. So again, we're done. That one's pretty straightforward. Not bad at all. Recall from elementary calculus the fact that these series are what they are. And we're done. That one wasn't that hard. It just requires you to know the power rule and how to simplify factorials. You could probably also derive that on a desert island. But notice, for both of these derivations, if you wanted the cosine derivative as well, you'd have to do a similar calculation. But I'm going to show you the next one. Very simple. Gets the cosine for free. All right, so now we're going to be considering the derivative of e to the ix, properties of exponentials. This is just I e to the ix, which is, if we expand using Euler's formula, cosine x plus I sine x, distribute the I, which is minus sine x plus I cosine x, and this is very similar to what we did before in proving the addition formula. This is what we get for free, d by dx cosine x, that's the real part, and this is what we wanted, d by dx sine x. So we've actually shown two things. We've shown d by dx sine x is cosine x, just like before, and also d by dx cosine x is minus sine x. Pretty cool. I like this one. If I had to derive this on a desert island, I would definitely use this one. It's very straightforward, elegant, gets to the point. Hope you like it as well. There are a few extra steps I could write out, but when you get more familiar with this, you just start by considering the exponential and separate into the real and imaginary parts. All right. This next example is off the walls. I found it on the Math Stack Exchange. I was looking for one more wacky example because I don't want to just have ordinary examples in my videos. This one requires the use of the polar arclength formula, the inverse function theorem, and the Leibnitz Integral Formula. So we'll put these pieces together, see how we can get the sine derivative. Okay, arclength. So for an infinitesimal triangle of sides dx, dy, and ds, we know that ds squared in Cartesian coordinates is dx squared plus dy squared, but we could easily go to polar coordinates. X is our cosine theta, y is our sine theta. You can easily show that this is polar coordinates, dr squared plus r squared d theta squared. I've actually shown this in another video, and it's pretty straightforward as well. Just differentiate these and plug them in. And now we want to let r go to 1 for the unit circle. This becomes a cosine theta and sine theta. And this, well, r is not changing, so that's 0. And this is 1, so it's just d theta squared. This is unit circle. And it tells us that since arclength is positive, ds must be equal to d theta, or s is equal to theta. Now this is a special case of the formula s is equal to r theta, which you might have known from high school with r equals 1, of course. And great, so you might ask where we're going with this. Well, you'll see, it's kind of strange. Basically, what I did now just explains my unusual choice of having the arc length be called theta to make the math work a bit more simply, avoid defining new variables. All right. So, we have d theta is the arc length integral the square root of dx squared plus dy squared. Recall d theta squared is equal to dx squared plus dy squared. That's why I have this here. And we want to write this integral in terms of y, since y we define to be sine theta. That's the variable of interest for us. So we're going to take it out, take out the dy squared as follows. We have dx by dy squared plus 1. And we can simplify this further. Integral dy squared of 1 plus dx by dy squared. But now we need dx by dy squared. It's really not hard, not hard at all. Back to our definition. We had x is cosine theta, y is sine theta. So 1 is obviously cosine squared theta plus sine squared theta, Pythagorean identity. And this is x squared plus y squared. We're going to differentiate both signs with respect to x to obtain that 0 is equal to 2 times x dx plus y dy. Don't need the 2, divide by it. So now we want dy by dx. We'll just go ahead and solve this expression for it. It's pretty straightforward. So then we have dx by dy. So we move this term over there, cost of a minus sign. And then we want to divide both sides by dy. We can do that. It's minus x over y. And you might notice from a previous video, this is also a special case of the implicit function theorem. And this is minus x. No, I did it wrong actually. Minus y over x. And that's minus y. We want everything in terms of y. So we'll just solve for x in terms of y using the Pythagorean identity. No problem. And now we're going to square it up here. So it becomes integral of dy square root of 1 plus y over 1 minus y squared. All right, let's keep simplifying. Don't need this anymore. Can do some ordinary combination of fractions here. This is integral with respect to y of the square root of 1 minus y squared plus y squared over 1 minus y squared. These go away, so we have the integral of dy over square root 1 minus y squared. Now, everything's indefinite so far. Let's go ahead and put back the limits. Sorry, that was theta all along. I do apologize. And now we're going to write it as theta of y. And we're going to integrate from 0 to y. And to avoid confusion, we also introduce a new dummy integration variable as physicists by putting primes. And great, so now we have theta as a function of y. So what we want, though, is dy by d theta, which is obviously d by d theta sine theta. This is what we want. But we can't see a way to get that. We can definitely get theta of y. We can differentiate this with respect to y. It's kind of weird. We're going to need the inverse function theorem and the Leibnitz integral formula, which I'll write out for you now. Inverse function theorem. Says quite simply that dy by dx is equal to 1 over dx by dy. Now, this just looks like symbol pushing, doesn't it? Isn't it just a simple application of the Leibniz differential notation? No, it's not. It's a theorem. We'll show you why. Example of the theorem. So let's say we wanted to talk about y is inverse sine of x, and I want d by dx inverse sine of x. Well, if we do this, then sine y is equal to x, and if I start computing dy by dx to be 1 over dx by dy, which I can compute by differentiating this expression by d by dy. So it tells us that dx by dy equals to sine y, which is cosine y. And now I can use the Pythagorean identity to write it in terms of sine squared. And sine squared is nothing but x. Square root of 1 minus x squared. So it's just 1 over square root of 1 minus x squared. Definitely seen this before. Probably derived the same way in calculus class. This is the best way to do it, in my opinion. And this just shows you that the statement of the theorem is non-trivial, since it can be used to derive results that you probably have to use Taylor series expansion to get, which we don't need. Okay, that's one puzzle piece. We also need the Leibnitz Integral Formula. For that, I don't know if there's a t in there. I keep forgetting. I don't know. This formula tells us if we have integrals with respect to parameters and want to differentiate them, we can do so as follows. The derivative with respect to the parameter of varying limits a of x and b of x with respect to some other variable integrating some function of x and t, so we have the variable and the parameter. This is just going to be function evaluated at the top limit times the derivative of the top limit minus the function evaluated at the bottom limit times the derivative of the bottom limit. Sorry, that's an x derivative, and that a looks like crap. Plus the piece that usually matters, just bring the partial derivative inside. It's not the case here. We don't care about this term. We actually care about these two terms, since we have the limit varying. We want to take d theta by dy, and y only appears here. We just have a constant here with respect to the dummy variable. All right, let's apply this. So we want to compute dy by d theta. That's okay. We don't have y by theta, but we do have theta by y. 1 over d theta by dy, which, let's quickly compute. Okay, what is d theta by dy? I'll save you some trouble. This term is the important one, since we have the lower limit not depending on the parameter, which is y. And we have the integrand not depending on the parameter y either, so this is gone. Only term left is this one. So we evaluate the function at the parameter and multiply by the derivative. dy by dy is 1. So we're just going to multiply by 1. We evaluate this function, this integrand here, at y. That's all we do. 1 over square root of 1 minus y squared, which is simply square root of 1 minus y squared, which we recognize immediately as, let's see, sorry, 1 minus y square root of 1 minus sine squared theta, which is cosine theta. And we're done. We've shown that dy by d theta is cosine theta in probably the most convoluted way possible. If you know of a more convoluted way, definitely leave a note in the message. I'll definitely include it. And if you want to see more, feel free to subscribe. See you next time.